Greetings, everyone. I'm going to go over the homework on solving congruences. So number 12 was the first one I assigned, and 12a was solve this 34x is equivalent to 77 modulo 89. Yeah, I noticed that the textbook sometimes writes this modulo 89 in parentheses. I'm not entirely sure why they do this. Sometimes they do this, sometimes they don't. Again, it's as common to write it without parentheses than with this, so I'm just going to stick to this. Now, in 12, they say use already exercise 6, but okay, I'm going to therefore also work out exercise 6, where we then find the inverse, because what we need is the inverse of 34 modulo 89, okay? So, step 1 is the inverse of 34 modulo 89. Now, how do we do this? We do this by using the Euclidean algorithm. So we're going to divide 89 by 34. That will be, and we're going to circle these things because we're going to have to do the backwards Bezout form. We really need the Bezout form to find the inverse, right? So this is 2 times that is 68. And so what we're missing still is 21, right? 89, okay, so 21. So then we do 34 divided by 21. That goes there one time, and the remainder is 13. 3, 4, okay. Then we do 21 and divide by 13. That also is there one time, and the remainder is 8. Then we do 13 divided by 8. That is 5. 8 divided by 5. That is 3. You see, sometimes it can go very slowly in the sense that you have to do quite a lot of steps. 5 is 3 plus 2. Right, 1 times 3 plus 2. Then 3 is 1 times 2 plus 1. And so now we got our GCD, which has to be 1, otherwise we are in trouble. Okay, so now we can work our way back. So this is step 1. Okay, step one, part 1, because now that's this direction. Now we're going to go back up this direction, right? So 1 can be written as 3 minus 2. We use now this one to rewrite the 2. That is 3 minus 5 minus 3, which is 2 times 3 minus 5, right? Okay. So now I'm using this 3. That is 2 times 8 minus 5. That's the 2, yeah, minus 5, right? Yes. So that is 2 times 8 minus 2, so minus 3 times 5. So by the way, you can at any time do a sanity check. What I mean is, if you have the time of it, to see whether you actually keep getting 1. If you make mistakes, 2 times 8 is 16, 3 times 5 is 15. So yes, this is 1, right? So this, whatever you write here is always 1, right? Now, if we trust ourselves, we don't have to check this, but yeah, sometimes you think, okay, did I do it right or not? So I'm going to check it. So now I use this to replace 5. So 2 times 8 minus 3 times 13 minus 8. So that is equal to, I'm going to write it up here, minus 3. That's with the second one has coefficient 3, and the first 8 has a coefficient 5. So altogether, minus 3 times 13. And by the way, this is 40 minus 39, so I'm still good. I'm now using 8. That is 5 times 21 minus 13 minus 3 times 13. So that is equal to 5 times 21 minus 5, so minus 8 times 13. And I think I'm still okay. So now I'm going using 13. That is 5 times 21 minus 8 times 34 minus 21. Right? That is 13 times 21. Oops. 13 times 21 minus 8 times 34. And then finally, I use 21, and that is 13 times 89 minus 2 times 34, minus 8 times 34, and so going back down here, we see that 1, because all these times is 1, right? Where does this 2 come from? 13 times 21, right? I don't know where this 13 came from. So that is 13 times 89 minus 26 minus 8, so minus 34 times 34. Now, checking that all my numbers are correct at this point by 89 times 13, that is 1157. 34 times 34 is 1156. So that is still correct. So this is correct. Now, that's step 1. Do we have the inverse? Yes. From this, no, remember, this means now that this is equivalent to minus 34 times 34 mod 89. Right? So I'm not need to circle things anymore now, because, so remember, modulo 89 means whenever you have a multiple of 89, you can ignore it. So we see that the inverse of 34 is minus 34. Now, that is actually not a number in the range. So we have to still do mod 89 of this number. So you see sometimes negative numbers appear because we need to make them always between 0 and 1 minus the modulus minus 1, right? So this is when we get a negative coefficient in this calculation in the Euclidean algorithm, you get a negative number. It is true that minus 34 times 34 is equivalent to 1 mod 89, but if you want to have the exact number, you have to find this the number mod 89. Now, what you can do is simply add 89 to that. So if I do plus 89, because that doesn't change the value of modulo 89, then you get, so in other words, I subtract, that is 55, right? Yes. So the answer is, so the inverse of 34 is 55 modulo 89. It is also minus 34, but we want to get a number that is, it's not really necessary, but in case you want to know what is the number, that's why I calculate. It's not necessary, because now, what is the step 2? So let me rewrite we have 34x is equivalent to 77, right? Mod 89, yes. What we now do is multiply both sides. So multiply with inverse. I can multiply here with minus 34, or I can multiply with 55. The result is always the same. So this is 55. I'm going to multiply with 55. I prefer to work with positive numbers. That's just me. So what is the result? Well, this one has to be 1, because that's the whole point, that we calculated this to be 1. So this is 1, so x is equivalent to, now 55 times 77 is 4,235 mod 89. So now we still have to find the exact value between 0 and 88. So we do 4235. How many times can I put 89 in there? So I divide this by 89. That is 47 times. And so 47 times 89, that is 4183. And we subtract that from 4235, and the result is 52. So the answer is, so this is equivalent to 52 mod 89, and this is now our answer. X is 52 mod 89. And we can check this. So what is 34 times 52? Let's calculate this. 34 times 52, that is 1768. Is this equivalent to 77? How do you check that this is equivalent to 77 mod 89? It's very simple. To check an equivalence, you don't have to, you say, okay, I calculate this mod 89. Sure, but you can do it simpler. You can do this. You take the difference, 17.6 minus 77, and that should then be divisible by 89. So let's calculate what that is. that is 1691. And now divide this by 89, and we see that this is 89 times 19. So this shows you that this means that 89 divides this difference, and that's exactly the same as saying that these two are equivalent. So we can check also. Okay, so there are two more to do. I'll take my time to solve all of them. Sorry, I jumped here. What was it? Next one, 144x. Okay, let's go back in black. So B, 144x equivalent to 4 modulo 233. So step 1 again. We first need to find the inverse of what? Of 4 of 144? Of 144, the one in front of x. That's the one that we want to multiply away. So, sorry, we don't. You have always to take the biggest one, right? So I wrote the wrong one. So I'm going to do 233 and divide it by 144. That is only once, so I don't want to make mistakes. I'm going to use my calculator here. 233 minus 144, that is 89. Again, since this is always going to be the stuff that I want to. And then the next one is 144 divided, that's 1 times 89. And the difference is 55, that's going to be 55. Then we have 89 is, okay, 1 times 55. They gave us a couple of nasty ones, I guess, in the sense that it takes for a long time before it goes down. So now we do 55, that is 1 times 34 plus 21, right? 55, yeah, 21. So then 34 is 1 times 21 plus 13, 34, okay. 21 is 1 times 13 plus 8. 13 is 1 times 8 plus 5. 8 is 1 times 5 plus 3. 5 is 1 times 3 plus 2. And then finally 3 is 1 times 2 plus 1. And here is our GCD. But we have to work our way back a lot. So this is going to be, so this is the downwards. Now we go back upwards again. So this is 3 minus 2. And then we use this 2 to write this as 3 minus 5 minus 2. There's a lot of negative signs, so always use a lot of parentheses here. So this is equal to 5 minus 3, what I'm writing here. So we have a 3, so it's 2 times 3 minus 5. I now replace this 3 by 8 minus 5. So it is 2 times 8 minus 5 minus 5. So that is 2 times 8 minus 3 times 5. Double checking that everything is 1. Yes. So now I use this one. That is 2 times 8 minus 3 times 13 minus 8. That is minus is 5 times 8 minus 3 times 13. Everything is still okay. But by the way, it's very much, you see the beginning is kind of the same as the previous one. But okay, we could have used that, but I'm not going to do that. So now we replace 8 in this expression. So that is 5 times 21 minus 13 minus 3 times 13. So combining that is 5 times 21. And I have minus 5, so minus 8 times 13. Is everything still okay? Everything is still okay. Yep, then I use 13. So that is 5 times 21 minus 8 times 34 minus 21. So this is 13 times 21 minus 8 times 34. I use 21. It's 13 times 55 minus 34 minus 8 times 34. That is 13 times 55 minus 13 minus 21 times 34. Okay. 34, 1355 minus 21 times 89 minus 55. So that is 13 plus is 34 times 55 minus 21 times 89. And then finally, that is 34 times 144 minus 89 minus 21 times 89. So that is 34 times 144 minus, what do we have here? 55 times 89. Now, hopefully everything is still okay. 34 times 144, that's 4008. So this is 4896, and 89 times 55 is 4895. Okay, so we are good. We have written our, so we write again. So 1 is equal to 34 times 144 minus 55 times 89. So this means, now we're working, what are we doing? We are, I forgot that there's an extra line here. Sorry, we're not done. Sorry. Okay, so we have, I was wondering, I don't recognize the numbers. So 34 times 144 minus 55 times 233 minus 144. Okay, and then so finally this is, so what I really need, this is correct, but it's not what I need. This is, you have to go all the way to the end, right? So 1 is now equal to, we have 34 and a 55, so 89 times 144 plus 55 times 144. What did I do? What am I? No, minus 5. Yeah. Where am I getting this one from? Sorry. No, let me rewrite this. Okay, so we had 444s, okay, and then how many times 233? Minus 55 times 233. Okay, now we're good. And this is, what we're doing, we're looking for 144 mod 230. So we're working this modulo 233. This means that this term disappears. So we have 89 times 144 mod 233. And this tells us that the inverse from what, this is the inverse. In particular, we have now our equation 144. So now that's step 2 if you want. Now we're solving it. 144x is equivalent with 4 modulo 233. I'm multiplying both sides with 89. So I do this so I put 89 here and 89 here. This one is 1, right? That's the whole point. That's, well, here it says it's 1. Okay, so x is equivalent to, so 89 times 4, that is 356 mod 233, and that is, it's a small number, you just subtract 232, so this is same as 123 mod 233. Remember, we should always give our answer within Z2, so remember, Z233 is all the remainders, that's from 0, 1, all the way up to 232. Okay, 123 is one of these numbers. Okay, and then finally, the last one was 200x equivalent to, so this is C, 200x is equivalent to 13 modulo 1001. So we do step 1. 1001 is 5 times 200 plus 1. Oh, look at that. We have our CGD right away. Sometimes things can go very quick, right? This already is giving me the GCD, and therefore the Bezout form, namely 1 is equal to 1001 minus 5 times 200. And so if you do this mod 2001, you get minus 5 times 200 mod 1001. So minus 5 is not within the range, but so what it would be, so minus 5 is equivalent to, now you're at 1001, so that would be 996, right? Mod 1001. Just to have the number within the range, the remainders, range of the remainders. But I want to show you that it's actually sometimes easier to work with a smaller number in absolute value, although it's negative. So let's multiply both sides with negative 5. So negative 5 here and negative 5 here. There's nothing that prevents me from doing that. And the point being that minus 5 times 200 is 1. Okay, so this gives me what? This gives me that this equivalence is x is equivalent to minus 65, right? Minus 65 mod 1001. And now I can find the remainder mod 1001 simply by adding 1001. So this is the same as minus 65 plus 1001, which is, in case you want to know, I don't want to make a mistake, so 936. If I would have worked with this number, then I have to multiply this with 13, and it would be a bigger number, which I still had to reduce. So this actually saves me a little bit of work. So sometimes it is advantageous to work with a negative number, especially if it's like minus 2, a very small negative number. Okay? Right, and then, so the other one is going to be also a bit long, and so this was question number 53. Number 53, and this was about example 8. And I want to give a little bit of context because I didn't cover it in the lecture, but I think it is something you should know and be aware of, because this is something that is used in computer coding. And the issue is this: so we have the following numbers. We have this moduli that we're going to use, and the moduli that they propose here are 99, 98, 97, and 95. So it's very common to have things like this. These are numbers, 2-digit numbers, very close to 100, okay, to a 3-digit number. And what is the advantage now? So for instance, the number 123684, we can look at this number modulo each of these moduli. Okay, so let's do this. So what is this mod 99? This is, okay, they calculate this for us, so I'm not going to work out why this is. So this is explained in the example. So this is 8. So the same number. So the same number, but now mod, so the other one, so I'm going to do it mod all 4 of them, so let me write that first, because so mod 98, mod 97, mod 95. Now, first of all, I should notice that all these guys are relatively prime-wise. That, of course, this is not immediately obvious, you have to check this a little bit. This is 9 times 11, that's 3 times 3 times 11. So you have to look at the factorization of this number. This is a prime number, this one. So none of these have a common prime. That is not obvious, right? It's not obvious at all that you can just do this, but that's part of the setup. That is the case. So if we calculate these other numbers, this is 8, this is, sorry, I'm reading this wrong, because this is a little bit, sorry, this is 33 here. This is 33. It's this one that is 8. So let me make sure that I copy this right, because it's 8. This is 9, and this is 89. So what is the advantage here? The advantage is that this number, which is a 6-digit number, can be represented by these numbers, by this quadruple of remainders, because the Chinese remainder theorem says there is a unique solution, at least less. What is the, okay, if these are the moduli, so M1, M2, M3, M4 in the remainder, we're going to do this, right? We're going to do the Chinese remainder theorem with this guy, so we better set it up already. What is this M? This M is a number 89,403,930. So quite a big number, right? And how do we get that? Well, it's just the product of the moduli, right? So remember, that's how the setup was. So, the theorem says, the Chinese remainder theorem says that if you take a number modulo 99, 98, 97, 95, there is a unique solution that is for whatever you say, x, whatever you give the remainder. So there's in particular this one, 33, 8, 9, and 89. There is only one number x less than this number, less than this 7-digit, 8-digit number, right? There's only one x less than this number that satisfies these four conditions, namely that's the number. How do I know? Because I calculated it, right? So if I have the given number, it's easy to do. So likewise, I can do this for the number 413. So here we do this. So let me set this up here. 413, another big number, 456. And again, mod 99. Yeah. Okay, let me copy this. Oh, no. How does this work? Sorry, I've actually never tried to do this. Copy, paste. Okay, so mod 99, this is, according to the book again, this is a part I'm not really checking. So you have to work this out. They say this is 32, 92, 42, and 16. So again, there is one unique number x less than, so there's only one 6-digit number in particular that satisfies these four conditions. So these two numbers are uniquely determined by these pairs here. So we have the other pair is 32, 92, 42, 16. Now, if you want to, and the whole reason is to do calculations with huge numbers. Now, of course, these are not huge numbers. We are dealing here with 2 digits. So we have reduced everything to 2-digit calculations. That's the point. We're trying to do everything in 2 digits involving 6 digits. Now, in reality, we're going to do things with perhaps 4 or 6 digits here, and we work therefore with something like 20 digits, which most calculators cannot deal with. Calculators cannot deal with 20-digit numbers unless they store them using this way. So suppose we have this very primitive old calculator that can only do 4 digits. Okay? So imagine you have a calculator that can only store 4 digits. The goal is to add these two numbers. You cannot do that with the calculator. You cannot put it in because the calculator only accepts 4 numbers. So how are you going to find the sum of these two things? Of course, okay, we know how to add these two numbers, but the same is true, by the way, for the product. But I'm going to just work with the sum. Now, what do you do? So I'm still explaining that example, okay? And then we get to the actual problem. So what you do is you add these numbers. So we do 33 plus 32, but we work this out modulo the first modulus, which is 99. Now, if you work that out, that is 65. There's nothing to be done, right? So in most of the cases, we don't have to do anything. We work out the sum of the next two. We have 8 plus 92. So I'm taking these two guys. This is modulo 98, right? Now this is 100 modulo 98. But of course, that's the same as 2 modulo 98. Then we do the sum of the third entries. That is modulo, which is 52. This is modulo, what's the next one? 97, right? And then finally, we add the last two. So 89 plus 16, which is 105, which is the same modulo 95 as 10. Okay? So in other words, what actually I'm saying here, they don't write it up, but that's really what I'm doing. I consider these as elements in Z99, because that's how you add in Z99. These two elements I view in Z98, and that's how you add in Z98. This is the addition in Z98. 8 plus 92 is equal to 2 in Z98. Okay? And then, so if you look at it, if you remember our notation of Cartesian products, so we look at this as a number in Z99. sorry, I do not have enough space. I'm going to write it down here. So what I'm saying is, sorry, I go down here. These both these two tuples, where are they sitting? Well, the first entry is in Z99. The second one, and so we do this Cartesian product, in the Z98. The third one in Z97, and the fourth one in Z95. And so the claim is every 6-digit number, in fact, much better, any number less than this here, so in particular every 7-digit number, has a unique representation as a quadruple in this set. Right? Remember, these are the numbers. These are 4 tuples, where in the first entry, in this case 33, 8, 9, and 89. These are the remainders modulo the various moduli. Okay, and we then do the operations in each of these one by one. We add in here, we add in there, we add in there. That's what we do. And so what we have now? So we have done this using only 2 digits, right? 2 or less than 4 digits. Less than 4 digits. Yeah, you see, the worst king was we had 3 digits here. A couple of times a 3-digit number appeared, but not 4 digits. And we are trying to do that because we are imagining we are dealing with 4-digit calculators, right? Calculators that can only store 4 digits. Now we have to add these 3 things. So what we have found is this. What is this tuple? So let's see, what is the tuple that we have by adding these 2? We added these 2 and we found the tuple 65, 2, 52, 10, right? These are the results. This is where I get these numbers from. This is now the tuple that represents what? Represents the sum of this number and this number. That's what we're after. So in other words, if we can solve this, we know that this represents one unique number of less than 7 digits represented by these numbers. So what is it? And that is exactly what question 8 asks. So what is x? We have to solve this. (97) and x equivalent to 10 mod 95. So if we solve this system, then we will have our solution. Now, of course, the answer is going to be a 6-digit number. So in other words, what I'm trying to say, what it really is going on, and that's how it works, is sure, we can deal with 6-digit numbers or calculators, but the calculations take much, much longer. So we reduce them to calculations involving 2 to 3 digits, you see that, and only at the very end, when we produce the result here, we will have a 6-digit number. But all the calculations in between only involve calculations with 2-digit, 3-digit numbers. So let me show you this, that in what I'm just saying is true. So we're going to do, in other words, now the question is to do the Chinese remainder theorem on this system. Okay, so let's perhaps, this is the background. So what I want to do is, I want to get rid of stuff here because I have already done some calculations here, so I want to keep them. So let me erase everything here that we don't need anymore. This was just a setup, right? This was just setting this up. This we don't need either. Oh, come on. I have to erase here with the bigger guy. I don't want to erase this. Okay. So this is what I want to do. Okay. All right. So this is the guy, the one was solved. So let me put that back up all the way here. Okay, so now we do the Chinese remainder theorem. We have already our moduli. We have found m. So what's the next thing to do is we have to calculate the mi's. So what is m1? Now this is unfortunate because now these are the product of the remainder ones. So these are big numbers. So this is 98 times 97 times 95. Remember, that is how M1 is calculated. And unfortunately, we need the value of the M1 at the very end. So what is this? What are these numbers? So how do I get this? First of all, in case you forgot, M1 is a product of all the moduli except for the little m1. So everything except for 99, so the other three. So that is this thing, and so that would be 99 times 97 times 95. That is, as I said, these are going to be now big numbers. This is where big numbers come in. And we need them all the way in the end. I'll show you why we need them only in the end. But I'm going to write them down already. M2, that is 99 times 97 times 95. So the index here, 2, means everything except for little m2, except for 98. And m3 will be everything except for this guy. And m4 will be everything except for this guy. Okay? So this is 99 times 97 times 95. That is 912. 285. Okay, so I made a mistake somewhere. Wait. What did I do? 99 times 97 times 95. Okay, that is correct. So the first one I punched in wrong. 98 times 97 times 95 is... Oh, okay. This one was wrong. This was 903070. M3 is 99 times 98 times 95, and M4, let me write it up already, that is 99 times 98 times 97. Okay, so 99 times 98 times 95, that is 921,921,690, and this is 99 times 98 times 97 is 941,094. Okay. What is the next thing we have to calculate are the y's. So y1, y2, y3, and y4. But what are they? Well, y1 times m1 should be equivalent to 1 modulo m1. Or let me write it in general. So for each I have to solve this equivalence. In other words, I'm going to find the inverse of these numbers modulo mi. Okay. Now you say, oh my God, these are such huge numbers. No, but look, you're working only, so really consider what you have to do here. So let me write down the very first one. So y1, and what is m1? I'm not going to write this number. Let me write the original numbers. 98 times 97 times 95 modulo 99, right? Right? So little m1 is this guy. So what you get is one modulus comes here and the other ones come there. That's if you want to kind of, if you're a visual person, that is how you have to think about it. So now we have to solve this equivalence here. 1 equal that, or find the inverse. Now, of course, we can reduce these numbers. And here is where I'm going to use something that you might, again, it's not really how you would, how to say, it's a trick. It's a trick to, it's like a little shortcut. I'm going to use, and using that's why I explained it already before, is sometimes, because 98 is very close to my modulus, it's much better to represent this as what? Well, I can, another one, a number that is equivalent to it is if I just subtract 99, right? This is very much what we do with degrees. If I tell you 350 degrees or 345 degrees, do you know what that is? You say, oh, 345 degrees, what does that mean? Oh, 300, that, if I subtract 316, that is minus 15 degrees. So it's 15 degrees below the x-axis. So it's much easier to work with the smaller numbers than with the big numbers. So this is the same as minus 1 mod 99. And the same for 97. So what is this going to be? Well, subtract 99 from it and get minus 2, right? And finally, 95, that is going to be minus 4 mod 99. Now, I am allowed to do that. So let's replace this now. So we have a minus 1 times a minus 2 times a minus 4 mod 99. This is way much less work. This is equivalent to minus 8 times y1, right? It's still minus 1. But that's okay. So now I can say, okay, I have to solve this. So I have to find the inverse of minus 8 mod 99. Now, minus 8 plus 99, so that is equivalent to 91 mod 99. Okay, so this is the same as 91 times y1 mod 99. So now I'll go back to my positive number because I want to do the division algorithm, and division algorithm only, well, you should only use it for positive numbers. It's very tricky if you use it with negative numbers. So now I'm going to have to find the inverse. So I do 99 is 1 times 91. You say, oh my god, there we go again. But look, the remainder is very, very small. In fact, we kind of knew that, right? That's going to be the remainder. And so now we do 91. How many times does 8 go in there? 11 times, right? Then it's 88 plus 3. Oh, that's not bad. 8 is 2 times 3 plus 2. And then 3, that's often we get to this last step here, that is 1. So this is the GCD. So that is 3 minus 2. Using this one, this is 3 minus 8 minus 2 times 3. So this is 3 times 3 minus 8. That's clearly 1. And now we're using this one. So I should perhaps write this. I should have written it here. Okay, I'm going to write it here. So that is 3 times 91 minus 11 times 8 minus 8, right? My minus was a bit in the circle, but that's okay. So this is 3 times 91. And then minus 33 minus 1, so minus 34 times 8. 273, I'm thinking, yeah, I'm still good. And then finally, replace this 8 here, use this 8. So this is 3 times 91 minus 34 times 99 minus 91. So what is this now? This is minus 34 to 37 times 91 minus 34 times 99. Now, I want to make sure that I don't make mistakes, because then one mistake and the whole thing is, okay, because the numbers are off, then, okay, so 37 times 91, 3367. Let me write it down because I'm going to forget this. And then 34 times 99, 3366. Okay, good. So remember, the difference has to be 1, right? So where are we? So let me write it up. I have that 1 is equal to 37 times 91 minus 34 times 99. Now, what am I interested in? Mod 99. So mod 99, the first remains. So we have 37 times 91. 1 is equivalent to 30. Let me not write the circle anymore. Mod 99. So this means to solve the first of these equations. Right. So this is okay. This gives me y1 is 37. Okay. So I found now that y1 is 37. Now we have to repeat this for all of them. I'm sorry about that, but that's how it goes. It's a long work, but it's also, I'm going to ask you to do a Chinese remainder problem on the quiz. And I'm not going to make it this long and this big, but still, I want you to be able to practice this, right? Because it's always the same calculations. Okay, so this is the y1. Let's do the y2 in the same manner, right? It's a bit pity, all these calculations, but you cannot really use them again. I have to do them over again. But I hope you're convinced now that what looked a daunting task is actually not that much. So again, y2. What is m2? That is 99 times 98 times 95, and I have to work modulo 98, right? Okay. Oh, that cannot be 97 here. 99 times 97. Of course, it cannot be the same, right? It's remember, one of the guys here and the other was there. Okay. So, but I can again, sorry, this is y2. 99 mod 98 is the same as 1, right? 97 we already saw is minus 1. And, well, we didn't see that, but it's easy to see, right? And 95 is minus 3. So I do, again, my minus trick. Because, look, this is now 3 times y2 mod 98. So I have to find the inverse of 3 mod 98. That's no big deal. 98. So how many times does 3 go in there? I think 32 times. Because that is 96 plus 2, right? Oh, look at this. This is something that goes very, very quick. Here is 1. So 1 is 3 minus 2, which is 3 minus, and then replace this 2 here, 98 minus 32 times 3. So this is 32 plus 1, 33 times 3 minus 98, which is indeed 1. So what does this tell me? That mod 98, remember, that this is equivalent to 33 times 3 mod 98. So if I multiply, and you might even have seen that 33 was the inverse here. So this tells me that this is y2. Good. That was much less work, right? So hopefully the trend continues. And that's why I took the biggest one first, because that's the one that is going to actually cause the most headache, so to speak, y3. So y3 is 99 times 98 times 95 mod 97. And we have to, this has to be 1. But this is the same as 99 is the same as 2 mod 97. Remember, just subtract 97, right? Basically, I'm going to, for each number, subtract 97 from it. Then 98 minus 97 is 1, and 95 minus 7 is negative 2. So this is minus 4 times y3. Now, I want to work with a positive number, so I have to add 97 to 4, so that is 93 times y3. So this is now what I have to do. I have to find the inverse of 93 mod, let me write it up, 97. But no, look, 97, again, the division algorithm goes very quickly here, because 93 goes in there once, but then look, your remainder is so small that the next step is going to be very almost immediate. 92, what am I saying? That is, okay. I'm getting a little bit tired. It's 23, 23 times 4, which is 92 plus 1. Ah, there we are. We have it already. So this is 93 minus 23 times 4, and then 4 is 93 minus 23 times 97 minus 93. So we see that this is 24 times 93 minus 23 times 97. First, quick check. Don't want to make any mistakes here. I'm so well on track. 2232. So this should be 2231. 2231. Yes. So we are good. Now, we are working model 97. So this part will disappear. And we get 24 times 93 mod 97. So this tells me that y3 is 24. Remember, we were solving this here, right? We were looking for the inverse of 93. So that's 24. And then finally, I hope you're convinced that the next one should not be too long either. That's the reason why one picks numbers so close to each other. Because in these calculations, although the numbers are big, they very quickly reduce to small numbers. So we have now y4, that is 99 times 98 times 97 mod 95. And again, this has to be 1. So this is the same as y4. 99 is the same as 4. Just subtract 95, subtract 95, subtract 95. So actually, it's not really true. The number is actually a little bit bigger here. So it's 24 times y4 that we have to do mod 95. Okay, but still, 95. So how many times does 24 go in there? Okay, let's do it. 95 divided by 24. 3 times. So we have 3 times 24. That is 72. And so what remains is 23. That's a little bit of a nuisance, you might think. Oh my God, what a big denominator. What a big remainder. 72. Yep. Yeah, 72. So 23. Yeah, okay. But look, that is 1 times 23 plus 1. Ah, here we are. We have it. 24 minus 23. Remember, we always work our way down until we have remainder 1, because that's the GCD. And it has to be the 1, otherwise it doesn't work. Now we work our way back up. So this is, using this equation, 24 minus 90 plus, no, minus, yes, yeah, so minus, okay, so if there's a minus, I should put parentheses. So it is 95 minus 3 times 3 times 24. I'm a bit on the edge here, and that's why my handwriting gets bad, so I'm going to go up here. So this is equal to 4 times 24 minus 95. Yep, that's still correct. And then what? Then nothing. I'm there. Okay, because so we have now 1 is the same as 4 times 24 minus 95. So if I do this mod 95, the second term is gone, so 4 times 24. So I find that the inverse is 4 here. Okay, so we did all the numbers that are necessary. Now there's one big calculation. And I hope that you're convinced now, although these numbers were really big numbers, I haven't used these big numbers yet. So far, I have only working with numbers of at most 2, perhaps 3 digits, because once in a while you go over like 100, but that's about it, right? Okay, now and only now, it's unavoidable, I have to work with the big numbers, because eventually my answer is going to be a 6-digit number, right? There's nothing I can do about that. Okay, so let's get rid of all the calculations because everything is done. And now we have to just write down what does the Chinese remainder theorem tell me. Well, x is going to be, I'm going to write it up, a1 m1 y1 plus a2 m2 y2 plus a3 capital M3 y3 plus a4 capital M4 y4. A1, where are the a's? Remember, these are the a's here, right? So this is 65. This is the first of the A1s. Capital M1, that's the big number, 903070. Y1 is 37, that's not so bad, plus A2. A2 is 2, right? This is A2 times this guy, 912285 times 33, this guy. Then 51, I'm going to write here, times this guy, 921690, times this guy. I could, of course, I worked out the product, but I could have still written these numbers so that I still have to, I'm writing down only 2-digit numbers, but eventually I'm gonna have to calculate the actual number. So there's no point in postponing it anymore. And so then finally, that is 10 times this number, 941094, times this number, times 4. And what is this? I have to calculate this modulo, because this might be a huge number, modulo m here. So modulo 89,403,930. Okay. Now this is the part where you actually have a little bit of trouble, perhaps, with your calculator. I'm not even sure that my calculator can do it. So I'm going to try. 3070 times 24. Okay, my calculator gives me exactly what this is. So, okay, so it is 140879. Well, I have to add all these numbers, right? So, okay, I'm gonna try to add them all, but I'm probably gonna make mistakes. Plus, and then I do 2 times 912285 times 33, and I close the parentheses, plus, open the parentheses, 51 times 921690 times 24, close the parentheses, plus, and then one more parentheses, 10 times 941094 times 4, and this whole thing if I didn't make mistake, 2, 6, 3, 4, 7, 9, 2, 3, 3, 0. 2, 4, 6, 8, 10 digits, 2, 4, 6, 8, 10 digits. So let's try to read this number a little bit. So it's 2 billion, etc. Now we have to take this modulo this number, which is actually smaller, right? So let's divide this now by 89403,930. That is 29 times. So it's 29 times, let's call this number is m, right? I don't want to write down the whole number. So what is 29 times 89403,930? That is that number, and of that I have to subtract that from this other big number, 2,634,792,330. That doesn't sound correct. The answer is supposed to be, but I'm saying, okay guys, we're dealing with such big numbers, it's a bit hard here to actually find. The answer should have been, well, we know what the answer is because, I erased actually the setup, but remember, this was to represent a sum of two 6-digit numbers, which I knew it was. So I know that the answer has to be 537140. And it's not what I got. I don't know where I went wrong. I'm leaving that up to you. I'm never going to ask you to work with these big numbers. And in fact, I'm a little bit questioning whether my calculator can handle these big size numbers. The biggest size number is actually the very first one here. The other ones are slightly smaller because you see this is, well, this one is also rather big. These are the two big ones, these are the two smaller ones. But yeah, it's still, okay. So I have not completely solved the problem, but the whole point was to show you that calculations can be done, and in real life, that what does things like that. One uses numbers like this, but more digits, to reduce calculations with 20 or 30 digit numbers to calculations with 5, 60 digit numbers. And then eventually one has to put it back together, and that is basically, I mean, everything else is correct, right? It's basically calculating this big number here and then reducing it more to this big number. These are the big number calculations. So you can imagine what you do is you have this one supercomputer that can deal with huge numbers, and all the other guys say, okay, you rest, we will do the calculation for you, and then at the end you tell them, okay, tell me now what is this? Model that. Okay, and then he calculates it for them. So you could, that's a way of outsourcing the final calculation. Okay, I know this was quite long, but I wanted to spend time on this Chinese remainder theorem because you're going to get a quiz. And so this also, again, is a review of that.